Okay, so what we're going to talk about is we have these differential equations, some of which we can't solve either because we can't antidifferentiate them or because the antiderivative, or the derivative actually, is given in terms of data, but we still might want to be, we're still interested in the solutions, and okay, we can't get the exact solutions, but maybe we want approximate solutions. So the easiest method we have of approximating these solutions is what's called Euler's method, and we'll give an introduction to it here. So first of all, we must write down an abstract differential equation, and it'll be first order, so it'll be about the first derivative rather than the second derivative. So what we will run with is dy dx. That's the derivative of y with respect to x, is given in terms of x and y. So this big f of xy is just nothing but a formula in x and y. And the other thing we're going to do is we're going to give an initial condition which says that at a specific point x0, the y coordinate is y0. Typically in context, that would be a starting time being 0 and the starting value of the velocity or the displacement or whatever. Okay, so suppose that you can't solve it, or even if you can, what can we say about the solution? So remember, the solution of this, the solution is y as a function of x. We're basically looking for y here. It's very important. So we're saying, oh, a function is basically a graph of a function, something like that. So does the differential equation give any information about the graph of the function? Sorry, I'm just closing the windows at the back. And well, what you have is one point on the curve certainly given by the initial condition. So at x equal to x0, this, y is equal to y0. So that's one piece of information that you know about the solution. And there's one other piece about the information that you know, is that you actually know the slope of the solution at that point. Because remember, dy dx is nothing but the slope, and the differential equation gives the slope in terms of the x and y coordinates. We have a specific point, x0, y0. So if we substitute x0, y0 into this formula, we will have the slope at that point, or the slope of the tangent. So we know a tiny little thing about the solution, and I'm just going to check, do we do it on the next page? Yeah. So we know a little bit, we know kind of the slope. So the slope of the tangent to the solution, we know that. So we have that the slope of the solution, or really the slope of the tangent to the exact solution, is equal to the derivative, which is some formula in x and y. Here it'll be x0, y0. Now what that means is we have a point in the slope, we can find the equation of the tangent to the solution at the initial point. Okay. So the differential equation, even if you can't solve it, gives two pieces of information. It gives a starting point and the slope at that point. Okay. So together with the point and the slope, you can plot the tangent to the solution there. Okay, that's fine. So in the two, this is what I've just said, we know two bits of information: a point on the curve, that is here, and the slope of the tangent, and I'll draw on the tangent. Okay. Now the thing about differential equations, a lot of them, the solutions are what we might call smooth or nice. So they don't have jagged edges, and in particular, what it means is that if you zoom in on one of these curves, for example here, or particularly here, the curve looks like a straight line. And so near a particular point, the curve is well approximated by its tangent. And this is what we have written here. With the tangent, approximately, we know about the local behavior of the solution. Now what local means is close to that point, and we know roughly what the solution looks like there. If you zoom in close enough, roughly it looks like a straight line. This means that for values of x that are close to x0, so maybe we might specify again that this is starting point, x0, y0, And we know for values of x close to that, like if we just come over, say from here to here, we can use the tangent to predict what's going on. And that's not too bad. Now the problem is, as soon as we move away from the local to maybe over here, the tangent and the curve are no longer very close together. And so this approximation using the tangent line to approximate the exact solution isn't very good. Okay. So I think what we're going to do is we're going to write down the equation of this tangent line. So we have a point and we have a slope. We use the y minus y1. Obviously the point x1, y1 will be x0, y0. And the slope will be big F of x0, y0. So you end up with this thing here. So you do put in x0, y0, big F of x0, y0. You end up with this little equation here. Okay, now what we're going to do, or what we could do, is suppose we want to move a little bit along the curve. Now what I mean by this is, so this here is the point, now this is originally a label x for that axis, let's just change it to x0. If you want to move along a little bit through a distance h, so this will be called x1. And x1 is the original point plus a step, and the step size we use h. And what we can do is we can estimate the true solution, which if we go dot 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 up in here, this is the true solution. Let's take this point over here. This would be x1. Now I wouldn't call the true value of y y1. That isn't really appropriate. It would be y of x0, y of x1. Okay. Now what we want to do is we want to use the y according to the tangent to estimate this. So if I draw a line up to the tangent, this is, so kind of making it explicit. This is y1, and y1 is like the tangent approximation to the true solution, and the true solution at x1 is y of x1. Something like this. So it's not the greatest drawing of all time, but so we're going to use the value of y according to the tangent to approximate the value, exact value of y, like so. Now we have the equation of this line, which we can write down. So this is the y coordinate is equal to y0 plus big F of x0, y0 times x minus x0. We did that below. And we're interested in what is going on with this line at x1, which is equal to x0 plus h. So I just need to plug in x0 plus h into this. Let's see what happens. So if I do that, it kind of explains what happens below. So y1, which is this tangent approximation using the tangent line, is equal to y0. Okay, and what we have is, if we're putting in x to be x1, that's to say that x is x0 plus h, you have x minus x0 is equal to h, so this thing up here is h. So you have plus f of x0, y0 times h. Now just to be consistent with what stuff we're going to do later on, or maybe I'll just check, I think we're usually going to put the h, we're going to write this the other way around. So y1 is the previous y value plus the step size, and remember big F is the slope times the slope at the previous point. There is an alternative notation that we will sometimes use here that says that the next point is the previous point plus the step size, And this is the slope, so we'll use y dash for the slope, y dash of 0, the previous slope. So this is our basic, this thing down the bottom is your basic Euler method. It says if you want to approximate a true solution using a tangent line, if you're going one step away, what you do is you say the next y value is the previous y value plus the step size times the previous slope. And this is the big idea you have to catch, is simply this: the next y value is the previous y value plus the step size times the slope. Here it's been derived. Okay. Now what we do, and we'll probably show it in this picture here, is that, okay, that's at x1. What if I want to go to the next point? So I have x0 here, x1 here, and I go another step here. Maybe this, now here the picture isn't great. So this is x2. If you want to find out what's happening at x2, so this here is the point x2, y of x2. Now what you do is kind of subtle. So you go, this is where you started, and this is where you end up after one step. Now what you want to do is, now you've already got an error, which is called a local error. We'll get to this a bit later. You've got a difference between these. Okay, so that's going to affect what goes on next. But what we're going to do is we're going to try and estimate what's going on here, and we're going to jump from here. And how we do it is we estimate, according to the differential equation, what is the slope at this point. Now it might be, it hopefully is similar to the slope here, but the differential equation will tell us what the slope is here, and then we kind of draw, it's not really a tangent anymore because you're not on the curve, but it's certainly a line segment. And say the slope, maybe it's the same as above, you'll travel along a line segment like that. I might take this, draw another picture on the left here in a moment. So what the Euler method does is it picks a step size, and rather than trying to, or well, you can find the exact solution, it goes along line segments. And the thing is, how does it know what slope to use? Well, it looks at the differential equation, which says what the slope should be at that point. If this was on the solution, what would the slope be? And it travels along that slope. And what you can show, and maybe we'll do it in a second, or maybe not, is that if you want to get to the next y value, it's always going to be the previous y value plus the step size times the previous slope. And that is what Euler's method is. So we'll try and draw a schematic of what we're going to be doing just on the left here. So you can have a true solution, something like this maybe. And what we're going to do is we're going to chop the x variable into little steps. So maybe we'll be going, say the starting point is correct. So x0, x1, x2. These will be equally spaced, and the space is called the step size h. And what we're going to do is we're just going to try and track the true solution by traveling along little straight lines. So say maybe from here to here, you do something like that, straight line. Then you stop and you change direction. You say, well, if this was on the curve, what would the slope be? Well, you have to ask the differential equation that, and say maybe it goes something like that. Go to the next point, you stop, ask what is the slope there, travel along a line segment, travel along line segment, stop, travel along line segment, something like this. Now the discrepancy between these two, this is the error. How much error you accumulate at each step is called the local error, and at the very end the difference between these two is what's called the global error. Now actually a lot of this we will be going over again, possibly in week 3, possibly in this series of videos. So this is what we're doing, and all day long, and it's definitely written on the next page, the next y value, say you want to find this y value, it's the previous y value plus the step size times the slope. You might have to see an example to understand exactly how it works. So you repeat the trick to go from x1, y1, and what you will find, so you start at x0, y0, you get to x1, y1 using the actual tangent to the solution curve, and then you say where you were, this is your approximation, you find that the next y value is the previous y value, which is y1, plus the step size times the slope at the previous point. Sometimes we will also use this, instead of the big F, it's also y dash, so this is the same thing as y1, so the previous y value plus the step size times the slope at the previous point. And then we get this little formula. So this I plus 1 signifies next y value. I, in that case, is previous. Now you could say, well, you could say previous next. You could say current next. You could say current previous. But anyway, there's a difference between them. I like the next y value is the previous y value plus the step size times the previous slope. Okay. So here's a little picture that is kind of describes what's going on. You probably have to look in your manual to see it. You mightn't see it here. So here you have a small range of values. Now what the hell is that about? Well, this is the point. If I go directly underneath, this is x0. And if I go underneath here, you'll probably have to go into your manual to see this. This is x0 plus h. So saying over us, this is just the original theory really. A small range of values x0 to x0 plus h over which the tangent is a good approximation. Now rather than continuing along the tangent, we stop and ask what should the slope be now. And as we said, this is the point here, x1, y1. The slope at this point well, it's dy dx is equal to a function of x and y. You just bang in those numbers. And the alternative notation is this is the slope y dash 1. Okay. So we're just going to go. Okay, we're just these pictures are actually kind of going over what we've done. So here we see the picture like this. The tangent at x equal to x0. So this is x0 here. Estimates the y value at x1. So that is the point here. So this is the point x1, y1. We call this y value by y1. I've just done that. And y1 is an estimate of the true value of 1. So this here represents the exact solution. And so if you go above this little point here, this is the point x1, y of x1, and this y1, which is not the point on the curve, it's the little point on the little line segment. Well, those y values are close together, it's a good approximation. Now we use the slope, which we know from the differential equation, and this point to approximate the tangent. So this little bit here is an approximation to the tangent at the true solution, which again should allow us to approximate what's going on at x2. We continue in this fashion to generate approximations at various different points. Okay, so maybe we should look at a specific example to help us understand what's going on. Okay, so here we have a differential equation. Now, as it happens, this can be solved exactly, which is good to show us, to analyze the error. So it says that the derivative of every point actually just depends on x. There's something good about that. And we know that initially x is equal to 0, at x equals 0, y is equal to 1. And we're interested in what's going on between 0 and 4. We're going to use step size of 0.5. And what that means is we might just draw something. We are splitting up the x between 0 and 4, see that, into 8 pieces. So that's 2, 1, 3. Okay, so this would be 0, this would be 4, this is 2, 1, 3. And all of these little things are little halves. So this is the step. So from here we're going to jump to here, from here jump to here, 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 here jump to here. Now the difference between the exact solution and what we have here is called the global error, and at each point, as the difference between the true solution and our approximations grow, how much that error grows is called the local error, which will be very important. We'll look at it a bit later. So Euler's method, now I'm going to use the y dash notation. So Euler's method says that the next y value, so I plus 1 signifying next, is the previous y value, so it's 1 back, plus the step size, which here is a constant 0.5, times the slope at the previous point. So, okay,